Thank you, Gian Maria, and thank you, Luke, first putting this nice conference together, workshop. I heard great things from my colleagues earlier this morning, and I echo their feelings about the workshop. It's been very fun and productive. And I'd like to especially thank you for having a YouTube stream. That's quite valuable, especially for someone like me with some childcare duties too. I could follow most of the talks on YouTube too. It is a lot easier to watch kids and YouTube at the same time than having Zoom going on. So I really benefited from YouTube broadcasting, and I think that's a great idea. It's like you can access on your smartphone or other devices. So that was really good. And also for this bunch of talks focused on a single topic, it was quite fun for me to follow them too. This is joint work with Sönmez Şahutoğlu, and I know we've seen a couple of different ideas around Bergman projection and the Neumann problem. And my particular topic today, my results are not related to Bergman projection, but all of them, our investigation started with Bergman projection, and we always fell a little bit short of getting back to Bergman projection. So that will be another theme that I will try to make. And I'll be more than happy to talk about various ideas later on, how we can push this a little bit more. I'll start with a quick introduction. I know we've seen lots of things, major ideas, major players in different talks, but nevertheless, I will start with a quick introduction. And I think of the talks we had in this workshop and overall the work in this area. There are three main players: domains, operators, and estimates. So probably in many of the talks, we heard different geometric quantifications on domains, like sometimes we look at smooth domains, and sometimes we look at singular domains, non-smooth domains, and the story changes quite a bit. Sometimes we have like things like finite type domain, or we have other specific settings like a Reinhardt domain that we will have a talk later on today. So there are some properties of the domains we are working on. And sometimes we want to keep them general, and sometimes we want to keep them very specific. For example, we just work on the Hartogs triangle. But we start with a domain. Then we have a bunch of operators. The main theme of this workshop is to look at the Bergman projection operator. And we also have just something very close to that Szego projection operator. These are objects that came up already in various discussions. And people familiar with these operators, it is nothing surprising that at some point, dbar Neumann operator N sub q will show up too. So if this is not something you use very often, don't worry. This is very much related to Bergman projection through Cohn's formula. But that connection, in this particular talk also, and in this particular work, we try to take advantage of that connection between dbar Neumann operator and Bergman projection, and it wasn't very straightforward. And that will be one of the points I'll try to make today. All right, in addition to Bergman projection, Szego projection, dbar Neumann operator, I will introduce also another operator, this inclusion map J. And I will tell more about this operator in a second, but this operator is also very common when you study dbar Neumann operator, especially on domains. So this is the inclusion of certain forms from one Hilbert space to one Banach space to another Banach space. And also we heard talks, and we know people working in this area, including many of us on this Zoom call and people watching on YouTube. We also look at Toeplitz operators and Hankel operators. And when we do Toeplitz and Hankel operators, in addition to this story of domains, operators, and estimates, we also have this business of symbols, right? Symbols come into picture, but today I will not go into any of those things. And now finally comes estimates. And as we've seen already this weekend and Thursday and Friday, we care about Sobolev estimates. Sometimes we think of them in terms of compactness. And sometimes we have LP estimates. And we already heard a couple of talks in the case where we have weighted estimates. So on these regular Banach spaces, we can also put some weights and try to understand these operators on weighted function spaces. So I think many of us, we really enjoy when we have theorems that are relating all these three things. We have a particular type of a domain, we choose an operator, and we obtain some estimates, right? And we want to understand how this operator controls the connection between the geometry of the domain and the estimates, analytic estimates on that particular operator we are studying. So this is the big, nice picture. And today I will mostly focus on this part. So I will refer to this whole big picture as a little bit harder analysis when you have some geometric information and you are trying to convert that to analytic estimates. That is usually hard analysis. And in this talk, we will mostly care about how we can just do some soft analysis around here. If we know certain estimates on certain operators, can we get certain other estimates on certain other operators? After all, these operators are related, right? So instead of going into hard analysis, instead of going into kernel estimates, understanding local geometry, how much we can push these ideas if we just use soft analysis techniques. So that's the general theme of this work. And I will say soft analysis is fun, relating operators to other operators. And sometimes you get interesting results out of them. And sometimes you need hard analysis to push the boundaries of this whole study. So I'll put them all together in this particular setting. All right. So before I move on, I'd like to mention a couple of estimates more in particular. And the first one is subelliptic estimate. The reason this is, of course, subelliptic estimates on the dbar Neumann operator. And the reason I wanted to start with this, we know this analytic estimate has a very nice geometric characterization. We know that subelliptic estimates are equivalent to, of course, on smooth domains, smooth pseudo-convex domains. We know this is the same as saying the domain is finite type, right? And this is probably, if I go back to my previous slide, in this whole hard analysis relating domains, operators, and estimates, this is one of the prototype results for us. We have subelliptic estimates if and only if we have finite type. And in this setting, we can also try to do some soft analysis. And with that, I mean, before that, let me mention a couple of things. For example, if we know we have subelliptic estimates, then we have automatically compactness of dbar Neumann problem. So I will put an arrow here just to keep things. I'll try to make a map. So I will need these arrows. So we know subelliptic estimates are equivalent to being finite type. And if we have subelliptic estimates, then we have compactness. And previously, Phil Harrington and we asked the following question. What happens if we assume subelliptic estimates? Can we get LP estimates based on subelliptic estimates? Because after all, subelliptic estimates are powerful, right? You gain derivatives. And in the LP results, many of we have seen also in these talks, we want to get some just LP to LP. Let's say we don't even care about any gain. So if we know subelliptic estimates, can we get LP estimates? This is also, you can also formulate this question directly if you can get LP estimates based on finite type, right? And if you remember just a couple of talks we have had in this workshop, we always, like people quoted results, it was finite type plus something to get LP estimates, right? And the reason for they needed little bit geometric properties to get kernel estimates to go to LP estimates, right? And those LP estimates in the literature on some subsets of class of finite type domains, they mostly involved kernel estimates, understanding the Bergman kernel or Szego kernel at off diagonal, and based on those estimates, one can get LP estimates. But can we get can we get any LP estimates from subelliptic estimates? Phil and I, we thought about this problem. And of course, ideally, what we wanted to have subelliptic estimates on the dbar Neumann operator and get LP estimates on the Bergman projection. And we couldn't do that. And we even wanted just LP estimates very close to 2. Let's say you don't want to get LP estimates from 1 to infinity. Just if you have subelliptic estimates, can you push it to have little bit, epsilon much LP estimates, something from 2 plus epsilon prime to 2 plus epsilon kind of a estimate. And even in that case, we were not able to do it, but there was a part we were able to do it, and I will mention that in a second. And that will also, I hope, will relate why these other operators come into picture in this whole understanding of this story. So we know subelliptic estimates, they have another equivalent characterization, and that is existence of good weight functions. This was true in the on smooth domains. Existence of good weight functions is equivalent to subelliptic estimates. This is in Catlin's work, but also Emil Straube showed that if you have good weight functions, you get subelliptic estimates also, even on Lipschitz type domains. So I will put just a single arrow here, and this is the case of Lipschitz domains. And what we were able to do with Phil was the following. Instead of subelliptic estimates, we started with good weight functions, existence of good weight functions, because this particular setting is more applicable to drive more estimates. And what we were able to prove the following: if we have good weight functions on Lipschitz domains, we were able to get some LP estimates. But LP estimates on which operators? We really wanted to get Bergman projection here. But right now, we don't have Bergman projection. We were able to get LP estimates on solution operators. So this can be dbar star NQ or dbar NQ. Depending on the form levels, you need to adjust form levels a little bit, but I'll write that much. So based on good weight functions, we were able to get LP estimates on these solution operators. These are canonical solution operators. If I go back to here, I could also add here that in this whole story, in addition to these operators, sometimes people also look at solution operators for dbar, right? And these solution operators can be the canonical ones or some other integral solution operators, right? And studying estimates on those operators are also quite relevant. So again, going back to soft analysis, if we have subelliptic estimates, how much LP estimates we can drive out of them, we were not able to do much except this part. We replaced the subelliptic estimates with good weight functions because we want, and we are working on Lipschitz domains. And by using those good weight functions, we were able to get LP estimates on these operators on Lipschitz domains, not the Bergman projection. All right, so that was what we did with Phil. I will mention another result. This is not the main part of this talk. Let's go back to now compactness. If we have subelliptic estimates on the dbar Neumann operator, then we automatically have compactness. And we know one more thing: compactness of NQ is equivalent to compactness of the inclusion operator J, right? So this J operator is common when you study dbar Neumann operator on domains, and you can use it in many effective ways. And now, in this particular work that I will state our result with Sönmez in a second, we will mostly think about this operator J, which is compactness of that is equivalent to compactness of the dbar Neumann operator. And we wanted to get some estimates, some LPs. Again, let me take a step back and say, again, like very much similar to my story with Phil, with Sönmez, we wanted to do some soft analysis right here. If we know compactness of the dbar Neumann operator, how much LP estimates we can get for free? by just using soft analysis. No kernel estimates, nothing. So that was our driving question. How much we can get on the LP scale based on compactness. And one reason we were hopeful for this, there's a result in the reverse direction by Haslinger. So I need to bring that up too, so I'll put it here. In this direction, from LP estimates to compactness, Haslinger has the following result very recently. What he proves is the following: if you have LP gain of on J operator, then you will get compactness. So I will be more specific later on, but I'll say this: if J gains LP scale at the LP scale, then you get compactness of J. Then J is compact. And remember, if J is compact, then dbar Neumann operator is compact. So there was some result in this direction. If you have LP estimates, LP gain on the J operator, then it converts to some compactness estimates on the J or the dbar Neumann operator. All right, so in this whole story, we were mostly, again, we wanted to go from NQ to P, but we were not able to do that. So very much like here, we looked at some other thing. So now I can go ahead and state my result. That will probably help me to explain what is going on rather than just saying this implies that. So here's our main result for today. We are on, so first let me highlight a couple of things. We are in C2. All right, so this argument, we were able to work that in C2. There are some versions of this that works in CN, but I will state the result in C2. We have a smooth enough pseudo-convex domain. So the technical smoothness requirement is C4. So omega is a smooth bounded pseudo-convex domain in C2 with required smoothness on the boundary. And here is our assumption. I assume N1 is compact. dbar Neumann operator is compact. I could replace this by J, as I said a little bit ago. So N1 is compact on L2. Then what do we gain at the LP scale? I wish we had Bergman projection here, but we don't. So our conclusion is the following. If you have a compact, if N1 is compact on L2, then this J operator is LP regular on these Banach spaces, DP, which I will define just in a second, but probably many of you, if you haven't, even if you haven't seen it, you can guess what I will mean by that, for all values of P greater than 2. So here as I said, if you want, you can put J here too. So this is a non-trivial property because in the same paper that we wrote with Sönmez, we also proved the following. If you can have an operator, let me just say this in the most generality, you can have an operator T that is from L2 to L2. And we know boundedness on L2 does not imply any boundedness on any other LP spaces, right? Even during this workshop, we've seen examples where you have Bergman projection operator, not just an arbitrary hypothetical operator. That Bergman projection operator can be unbounded on any LP spaces as if P is different than 2, right? So if you know boundedness, you cannot get LP estimates immediately. But what happens if you assume this operator is compact from L2 to L2? And again, you can cook up a counterexample that you have a compact operator from L2 to L2, but T will not map any LP spaces to any LP spaces. So it will be unbounded for any P greater than 2. So this is not a trivial consequence. It doesn't come from just very soft analysis that if you have a compact operator, then you have to have some sort of LP estimates immediately. This is not true. So that means this is a non-trivial property of J operator. All right. If you have compactness on the L2 spaces, then you have LP estimates on the appropriate P spaces. All right, so with this, now I will try to explain all these players and then go over the proof. So what do I mean by DP space and LP estimates on J? So let me a little bit be more specific about this. This is nothing too strange to many of us. So this story from L2 to LP, L2 story starts with Hermander. We know that if we are on a pseudo-convex domain, bounded pseudo-convex domain, then we can control the L2 norm of a form by the graph norm of the form. So I will write this explicitly because I will play on this little bit. So we can control the LP norm by the graph norm for any 0Q form F that is in domain of dbar and domain of dbar star. And now I will go ahead and do something. What we want, what I refer as LP regularity is, can we go back to this basic estimate and replace this 2 by P? Can we have P here? So that's what I mean by LP regularity. And in order to make it more concrete, I will go ahead and decorate these domains by 2, meaning that this is the definition, this is the domain as a subset of L2, and the adjoint is defined on the L2 space. So it is nothing too complicated to define a LP domain of dbar. So this is going to be exactly what you think that should be. And by using the weak differentiation idea, you can also think about adjoint operators domain in the LP scale. So we want to go from these spaces to these spaces. This is what I call capital DP. And in our case, since we are only working on 0-1 forms, we are in C2, this will be 0-1 forms on my domain. All right, and here, the graph norm in this setting will be, I will look at dbar F, and I'll take LP norm of that, and I will add LP norm of the adjoint. All right, so on this space with this graph norm, first you have to make sure this is indeed a norm, right? You have to make sure it is a norm, and then you have to prove closeness, right? You have to prove that this space is a closed space. And actually, closeness of that is equivalent to getting this basic estimate at the LP scale. So that's also equivalent. So in other words, our result here is saying these spaces, DP spaces, are indeed Banach spaces if P is greater than 2. All right. So what is the main idea in this approach? So as I said, this is a little bit soft analysis. Instead of going into hard estimates on the kernel or operators directly, we wanted to use compactness and some other soft properties. And the other crucial ingredient I will bring up just in a second is product rule. So product rule is actually what helped us with interpolation idea. All right, so this is dP and the graph norm, and I already stated the result. So let me say a little bit more about the ingredients. In order to prove something like this, we certainly need a density lemma, and this density lemma is quite standard in the C2, in the L2 setting. This is very familiar to many of us. And that is the following. I will work on these spaces dP, 0-1 of omega, but in little bit, I will start taking derivatives and so on. So I need to make sure functions that are differentiable up to the boundary, up to certain order K, should be dense in my space dP, right? This is the place where we need that C4 smoothness on the domain. If the domain is C4 smooth, then you can make sense of this K can be as big as 3, and you can prove that if you only look at functions 3 times differentiable up to the boundary, you will have density in these spaces, so you can safely do differentiation and everything. The second important ingredient is controlling the normal component. Again, this is very similar to the story in L2 setting. If you are on a C4 smooth pseudo-convex domain, and if you go ahead and take a function f in P space, again, if you want, just think of this as the 2 space, D2, domain of dbar and domain of dbar star together, then when you look at your one form, and if you look at the normal component of that, then you can control the Sobolev one norm of the normal component by the graph norm, right? You can control the Sobolev one norm of the normal component by dbar of f plus dbar star of f and f itself. And you can go over the proof in Chen and Shaw, and you see here you can go from L2 Sobolev spaces to LP Sobolev spaces, and you can put here LP norms without any issues. When you fill in the details, you will get this control. Again, the graph norm will control the Sobolev one norm of the normal component. And finally, we need something little bit more than control on the normal form, and this is specifically Gardner's inequality. Again, in the C2 setting, we are very familiar with this. If we have one form in dp01, and again, start with the case domain of dbar star in the usual L2 setting. And if we take a function phi that is 0 on the boundary, and if we multiply our form by that function, then we can control the Sobolev one norm of this product by the graph norm of f. But again, standard theory here is for the L2 spaces. You can go over the proof to see that you can modify it to LP spaces, and you can have this kind of an LP version of Gardner's inequality. All right, so these are the important ingredients. We have, in our setting, we have density. In other words, we can just work with functions smooth up to the boundary. We can control the normal derivative of the, we can control the Sobolev one norm of the normal component of a form we are interested in by the graph norm. And we can also use graph norm to control our one form times a vanishing function on the boundary. All right, so with these pieces all together, I can go ahead and tell you a little bit more about the proof and where that product rule comes into picture. All right. So the first thing, my starting assumption is N1 is compact. And we know that you can write compactness as an estimate for a very particular compact operator. And what we already know is the following. We will go ahead and use the following operator, K from our P space to P space. And what this will do, K of a form will be just multiplication by the defining function. This is, or the distance function. This is distance to the boundary. Clearly, it will vanish on the boundary, and therefore, this operator will be compact for any values of P between 1 and infinity. So by using this operator, now I can convert this compactness assumption into a working inequality, workable inequality, and that will be the following. So if you give me a one form, I can control L2 norm of that by just tiny little bit of the graph norm. And the big chunk, and the big constant, probably, I don't know, but not a small constant times the L2 norm of this compact operator acting on F. So this comes from standard Hilbert space theory. We can turn this compactness into an estimate like this. All right, so this is my starting assumption. And what I want to drive from this, I want to get LP estimates on this side. So I want to change all of these to P, if I can. So here I want to get LP norms where P is greater than 2. And as I said, this is not immediate, but in this particular setting, it works. And here our approach will be the following. When we will start, let me denote this function, switch to capital F to make it consistent with my notation in my notes. All right, so this is capital F. And remember, we are in C2. So what we will do, I will write this F as two different components, F1 with one form omega 1 plus F2, another coefficient times the second component omega 2. And we will assume this is the normal component. So this part of the form is one form F is the normal component. All right, remember, since F is in the domain, F2 is 0 on the boundary. So that will be really important to keep in mind. F2 on the boundary will be 0. All right, so I want to somehow get my hands on L4 norm of F. So I want to estimate L4 norm of F, but this is the same thing as L2 norm of F square. But I will take that square a little bit differently. So let me use a different color. I will define another one form, F sub 2. This will be F1 quantity square. Again, this one form, F2 quantity square, this form. So instead of just taking the square of the one form, I'm taking square of the individual components. And then L4 norm of F is the same as L2 norm of F2 quantity square. So this is where the soft analysis will start. And now I will go ahead and invoke compactness estimate for this new one form F2. And let's see what I get when I do that. So here, let me rewrite the compactness estimate for this particular one form F2. So L2 norm of F2 is controlled by a small constant times graph norm of F2. And now I will start writing L2 as a subscript to make sure I can keep track of everything. Then I have a big constant times K acting on F2. So this is the compactness estimate. And F2 is square of F. Remember, I want to control L4 norm of F, which means I want to control L2 norm of F. So left-hand side is okay. This is already pretty much L4 norm of F, right? But the problem is replacing L2 norms on this side. And that's where the soft analysis will come into picture, because remember, I had these one forms, this frame omega 1, omega 2 for 0, 1 forms. And let's say L1 and the L2 are the dual vector spaces differentiating in the appropriate directions. Then what is going to be dbar of F2? So let me write this down carefully. So this will be L1, this will be L1 acting on, so let me write in this order, the one I have, L2 acting on F1 square. Then I have to look at the action of L1 on F2 square because of the duality. So I have L1 acting on F2 square. So the L2 norm of this 2 form is the same thing as L2 norm of this function. And here we will use standard product rule. So this is the same thing as F1 acting times up to a constant, of course, F1 times L2 of F1 minus F2 times L1 of F2, L2 norm. All right, I can control this part here without these extra coefficients. So the rest of the argument will be, as I said, will be the soft analysis, adding and subtracting correct terms so that we can regroup the terms in a careful way and we can observe things to the left-hand side. So this is what I have for the first term here. Let me color this by purple too. So the purple term is this purple term here. And I will do the same thing for this second term. Let me color that by, label that by green. So what will be this green term? dbar star of F2, L2. Now this is a function, right? F2 was a one form. dbar star of that will be a function. And what will be this function? This function will be, again, L1 acting on F1 square and L2 acting on F2 square. So I need to look at the L2 norm of this function now. But again, by product rule, you can say product rule, chain rule. In this case, that will be equivalent. So I will get F1, L1 acting on F1 plus up to a constant F2 times L2 acting on F2. So what happened? Now I can control L4 norm of F or L2 norm of F2 by these terms. A small constant times I will write this, then I will start doing that soft analysis. F1, L1, F1 plus F2, L2, F2. Remember, I want to produce L4 norms on this side. So that is my main goal. I want to produce L4 norms here. So how can I get L4 norms there? At some point, I need to use Cauchy-Schwarz inequality, right? So that I can get L4 norms. But when I do that, I want to make sure the things I get in front of L4 norms, I can observe them. That's the whole plan for the rest of this game. You want to use Cauchy-Schwarz carefully, and anytime you obtain L4 norms on the things you need, they will come with an extra coefficient. And you want to take that coefficient to the left-hand side and add it into this L4 norm here. Of course, we will take advantage of this arbitrary small constant that will show up here and there, but this is pretty much the whole idea. Let me add this important term here too, C epsilon K acting on F2. So from this point on, as I said, we do some Cauchy-Schwarz inequalities, and we can observe the terms to the left-hand side. So this is what I refer as doing a little bit less than hard analysis by manipulating these estimates with Cauchy-Schwarz inequality and with correct coefficients in front of them. We were able to get the L4 norms here and L4 norms there. So this machinery will produce us. Let me add another page here. Okay, so I have one more page here. All right, using this kind of manipulations, we will be able to get the L4 norm we wanted. So we can, for one form, we will be able to get L4 norm of that one form can be controlled by a small constant times L4 graph norm plus another constant times a compact operator acting on F for any capital F in D401. So by just squaring the components, we were able to get L4 estimate, this L4 compactness estimate. So this P has to be 4 as well. So as you see, not just boundedness, we also obtained the following. J is compact on D401. All right, so this is how we started. Let me put a picture here. We started with compactness on L2. Then we were able to get, by manipulating the compactness inequality, we were able to derive compactness of J on L4. But now you can keep iterating this process. You can use L4 to get compactness on L8. And so on. You can get compactness on powers of 2. And once you prove compactness, you already have boundedness. Therefore, these spaces turn out to be indeed Banach spaces. So they are all closed non-vector spaces. And then they also form a nice interpolation sequence. Therefore, it makes sense to talk about not just L, D2, D4, D8, D16. You can talk about these spaces D as being Banach spaces for any P between 2 and infinity. And when with that interpolation argument, we are able to get the final result when J is compact, if N1 is compact on L201 of omega, then we have these J operator is LP regular. But now let me write what that means. You can control L4 norm of one form by it is graph norm. So this is not L4 anymore. This is LP, D bar F, LP plus D bar star F, LP for any P greater than 2, less than infinity, and where PF is in this Banach space, dP01 of omega. All right. So as I said, we had the reverse direction already in Haslinger's work. Haslinger's work was going in this direction. So now I can also mention in retrospect Haslinger's result. Haslinger's result was the following. If you have some LP gain here, LR on the left-hand side, if you can control LR norm of one form by its L2 graph norm, this will imply this operator J or N1 is compact on L2 of 0,1. So this is Haslinger's result, and ours is working in the opposite direction. If you have compactness, then you get these LP estimates on the inclusion operator J. Again, our result is right now, let me also put that in perspective again. Remember, omega is in C2, and I effectively use this assumption, right? When I decompose the function, one form capital F into two parts, F1 and F2, square F1 square and F2 square, and knowing that F2 is identically 0, I really took advantage of that, working on one forms and also on a C2 domain. This same argument will immediately give us the same result on P comma n minus 1 forms on domains are in Cn, but I will not mention that particular generalization of this result. But this is what we have on C2 domains. So now taking a step back, let me go back to the beginning. To here and finish by again saying in this talk, we were mostly interested in this portion of the story, how much estimates on various operators we can get when we have certain other assumptions on operators. Of course, domain structure geometry came into picture in our soft analysis too, but it was only at the level of making sure we have correct density statements and correct inequalities to run the soft argument. And as I said, I have done something like this with Phil, and now Sönmez and I, we did something. And ultimately, we were interested in this particular question. If you have good weight functions, or in other words, subelliptic estimates, which is quite powerful, how much LP estimates we can get, especially on the Bergman projection, if not on certain other operators. So with this open direction, I will conclude here. As you can see, there's a lot to do in this discussion. And this just, I hope, will bring another perspective rather than going from geometry directly to estimates, how much we can do, how much we can obtain by just manipulating estimates. And with that, I'll stop here.